Alright, so this is the second part of my video on exponential growth and decay. And here it says the function p of t is equal to p naught times e to the kt power. It says this can be used to calculate interest that is compounded continuously. So we've already talked a little bit about this. Really, it's the same as our PERT formula. It's just we're using, it's considered a more general form. Notice P of t is the amount in the account after t years. It's not a population anymore. P naught is the amount of money invested, or the starting amount. T is still the time in years. And notice instead of R we use K for the interest rate. So it's exactly what we did before. It's just using the general formula here. So I'd really encourage you to see if you can do this one. 2a is a little bit different, but it's going to be, when you solve it, you'll solve an equation similar to what we did on the last two slides. So see if you can set it up, at least try to set it up, and then you can always check the video to see that you're setting it up right. But ideally, I'd love for you to try to see if you can get the whole problem completed. Okay, so let's see how you did. So on number 2, it says here that $2,000 is invested at interest rate K. So in this problem, using our new variables, this would be P naught. And our interest rate we're calling K. That's what we're actually looking for here. And let's see, it is compounded continuously, so this is the formula we want to use. It's basically the PERT formula. It grows to 250465, so basically that would be our P of t, which we used to call A, after 5 years, and of course that's our t. So what's the interest rate? So first of all, you would want to write down the general formula. We know P naught, we know P of t, and we know t. So let's plug those in. We get $2,504.65. We'll write it without the numbers or the dollar sign. Equals 2,000 times e to the kt. That's just going to be 5k, or k times 5. I'm going to go ahead and switch the order in the next step, but so let's go ahead and divide each side by 2,000. So you're going to get 1.252325. So again, I'm carrying a lot of decimal places, and that's equal to e to the 5k power. So now we need to switch forms. This will be the log base e of 1.252325 is equal to 5k. Let's switch to the natural log form using ln, and then divide each side by 5. So you're going to get k is equal to 0.045. Now remember, that's an interest rate, so that would be 4.5%. All right, so now on B it says find the exponential growth function. Well, we know P naught, and now we know K, and so we can plug those in. We get 2,000 times e to the 0.045t. It says what will be the balance, or in part C it says what will the balance be after 10 years. So in this case our t is 10. So we're going to plug t into the formula, and when you do that, you get 3,136.62, or $3,136.62. So actually it's not a formula, it's really a function. Let's look at D here. It says after how long will the $2,000 have doubled? Well, if our money is going to double, it's going to go from $2,000 to $4,000. So let's go ahead and write down our function, and let's put in 4,000 for P of t. And so this is again very similar to the equations we've been solving. We want to divide both sides by 2,000. And we get 2 is equal to e to the 0.045t. And so this is exponential form. We're going to want to change this to logarithmic form. If you haven't already done that, you might want to try that. It's very important that you could change forms. So you should get natural log of 2 is equal to 0.045t. So let's go ahead and divide each side by 0.045. And so you should get 15.4. And so the answer here is going to be 15.4 years. It'll take about 15.4 years to double your money. And that's not great. I mean, 4.5% interest rate is not real high. On the other hand, these days it's hard to get a good interest rate. It'd be difficult even to get 4.5% right now. All right, let's move on to the next slide. And this will be our last problem, and this one deals with exponential decay. So let's go ahead and look at this problem. It says the radioactive element carbon-14 has a half-life of 5,750 years. So what that means is, let's say you had 100, I don't know what it would be measured in, we'll just say grams of carbon-14. Then after 5,750 years, you would be down to 50 grams, which would be half of the original amount. So that's the idea. It says the percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14 at the time it was found. How was the linen, or how old was the linen wrapping? All right, so basically we're looking for T. All right, so I'm going to go ahead and write down our formula or our function. And there's something important I need to put here first, and that is a relationship between the decay rate and the half-life. This is a formula that you'll see in the book. It's not too hard to generate it, but we have a lot of other things going on here, so I'm just going to give it to you. The decay rate K and the half-life T are related by K equals the natural log of 2 over T. And so let's go ahead and find K for our situation. So K is the natural log of 2 divided by the half-life, which we said was 5,750 years. And so K is, now on your calculator, you're going to get a number that's in scientific notation. And if you round the decimal part, it would be about 1.2 times 10 to the negative 4 power. Now remember, what you need to do to change that to a standard form, the way we normally write a number, is move your decimal 4 places to the left. And you're going to get 0.00012. All right, so now when we start plugging things into the formula, there's another part here that's a little bit tricky. It says that the linen wrapping had lost 22.3% of its carbon-14 at the time it was found. So P naught represents the amount of carbon-14 at, originally when it was let's see. It lost 22.3% basically of its original amount of carbon-14. That's what we would call P naught. So the thing about it is, if it lost 22.3% of its carbon-14, that means that only 77.7% is left. Just subtract from 100. And so here's how we're going to put the numbers in. It'll be 77.7% of the original amount, P naught, is equal to the original amount of carbon-14 times E. Oh, I know what I forgot to mention here. Notice I'm using a minus in front of the K. This is a decay rate, and so that's going to be a negative value. In fact, anytime you're dealing with exponential decay, you're going to have a negative value for the growth rate. And so this is negative 0.00012 times t. Now it seems kind of strange. We don't know what P naught is, but it actually doesn't matter. It was just the amount of carbon-14 that was originally in the linen wrapping. And so, but here's the thing. When we divide both sides, well, first of all, I'm going to go ahead and change 77.7% to decimal form. And then let's go ahead and divide each side by P naught. And so we get 0.777 is equal to e to the negative 0.00012 t power. So let's go ahead and switch forms. We get the natural log of 0.777 is equal to negative 0.00012 t. We'll divide both sides by negative 0.00012. And we're going to get t is equal to 2,102.6. So that's a lot of years. If you round, it's about 2,103 years old. And so that's how you would do a problem like this. You'll see one of these in the homework. All right, and we're going to go ahead and stop the video right there.